Dear student, today's session is 25th session of Graph Theory 2 on the topic planar graphs. In the previous classes, we have discussed many concepts, that is planar graph, outer planar graph, maximal outer planar graph and non-planar graphs. We took a characterization for those graphs also in detail. Okay. So now today we are considering some problems on planar graphs. Of course, the general results, the concepts already we have discussed in detail. Let me consider some problems on the planar graphs. The first problem is, suppose there are three houses and three utilities. The thing is that every house requires some utilities, for example, gas, electricity and water pipeline, water. Okay, so we need water, we need gas supply, we need electricity. So nowadays we are getting all the three facilities or utilities through pipelines, that is water pipeline, gas pipeline, even the electricity connection is also from the underground. Okay, so now the thing is that there are three houses and three utilities. So all the three houses require all the three utilities. It implies, if we consider houses as three vertices and utilities, say what we can say, electricity, water, gas in terms of vertices. Houses are also in terms of vertices and utilities are also in terms of vertices. So every house required all the three utilities. It implies we join the house H1 with all the three utilities E, W and G. Similarly, we join H2 with these three utilities. Similarly, we join H3 with all the three utilities. Now the question is that, is it possible to connect without the crossover of the conduits? Isn't it? It implies, so first let me consider the problem. Suppose we wish to supply three houses, each with three utilities, say electricity, water and gas. Is it possible to connect each utility with each of three houses without crossing of the utility lines? This is the question. Now, is it possible to join in that way? So we will solve this problem with the help of graph concepts or graph theory. So now what we will do, this situation can be represented by the graph shown in figure 1, in which the houses and supply stations are shown as vertices and utility lines are edges. The resulting graph is K33. It is a graph which is called a complete bipartite graph K33, which is non-planar. Already in the previous class we know K5 and K33 are non-planar. K33 is non-planar. So therefore, I think already you have got in your mind. So is it possible to connect without the crossover of the conduits? So therefore, the graph cannot be drawn in the plane without crossing of the edges. Why? Because K33 is non-planar. It is not possible to join without the intersection of the edges. It cannot be embedded in the plane. So that's why it is not possible to connect each utility with each of the three houses without crossing of the utility lines. So this is the solution for a simple problem in terms of graph idea. Okay, graph theoretic idea we can say. So now the second problem, draw a planar graph with 6 vertices and 12 edges. Such questions they may ask. Okay, even in the examination also they may ask, draw a planar graph with 6 vertices and 12 edges. So it is not compulsory to draw the same graph. You can think yourself and you may draw according to the question. So here is an example. We have considered 6 vertices, 1, 2, 3, 4, 5, 6. What we did, first we have considered one triangle type outside, and again inside we have considered another triangle with opposite shape type. Okay, then triangle outside already we have joined with 3 vertices. Even the inside triangle is also joined with 3 vertices. So how many, sorry, 3 vertices, it implies how many edges are there? Outside 3 edges, inside 3 edges, 6 edges, and 6 more edges to be considered. So what we did, so these 2 vertices with this vertex, now these 2 adjacent vertices with the other vertex of the exterior region, and these 2 vertices with the other vertex of the exterior region. Okay, just very simple. One cycle C3 outside, even inside also one C3 with opposite direction. Okay, and 2 adjacent vertices with one vertex. Similarly the other vertex, similarly the other vertex. This is how we got a planar graph with 6 vertices and 12 edges. Now the other third question is, draw a non-planar graph with p vertices which has 3p minus 6 edges. Okay, draw a non-planar graph with 3p vertices which has 3p minus 6 edges. Okay, so you have to think for that. Suddenly if you observe the diagram, if you observe the graph, okay, you may say that yes, this is the graph, right? But you need to think. So first you have to consider p vertices. That is, how many vertices are there here? Here you have to consider p vertices. Okay, yes, it is possible. P vertices which has got 3p minus 6 edges. If you recall one theorem, what was the theorem? Every planar graph, the number of edges in a planar graph with p vertices and q edges. What is that? If G is a planar PQ graph, means it is a graph with p number of vertices, then the number of edges q is always less than or equal to 3p minus 6. Is always less than or equal to 3p minus 6. And it is equal to 3p minus 6 if it is a maximal planar graph. If you recall or if you remember that statement very easily, you can draw. So the following graph of figure 3 has 6 vertices and 12 edges, that is 3p minus 6, which I have given one counter example for this. Okay, you can say in general, what you can say, draw a non-planar graph with p vertices which has 3p minus 6 edges. So generally how to draw? Consider in particular p is so and so, or you can say by one of the results, if G is a planar graph with p vertices, then the number of edges is always less than or equal to 3p minus 6. That would be the solution. But if they ask to draw, you have to consider a specific value for p. Here I have considered p as 6. Then what would be the number of edges? 3p minus 6. That is 3 into 6, 18 minus 6. So that should be 12. So a graph must contain 6 vertices and 12 edges. So this is the graph which is having 6 vertices and 12 edges. Okay, so this example is purely based on one of the results which we have already proved in the previous class. Okay, now let me consider another example. Draw an outer planar graph with 8 vertices and 23 edges. Draw an outer planar graph with 8 vertices and 13 edges, not 23, 13 edges. First of all, in your mind, if you consider an outer planar graph, what you should get? All vertices must lie on the boundary of the exterior region. It implies you must consider all vertices on the boundary of the exterior region. All vertices on the boundary of the exterior region. It implies it is a cycle with 8 vertices, like that. Okay, so that you should get in your mind. Then already 8 vertices if you join or if you form a cycle, there will be 8 edges. 8 vertices, 8 edges. So still we need to join some other non-adjacent vertices. Okay, so like that, if you join the non-adjacent vertices, then what you will get? You will get a graph, an outer planar graph with 8 vertices and 13 edges. Okay, so very simple solution for this problem. Okay, now If the question is like this, draw two graphs homeomorphic to the graph of G. One graph is given, you are asked to find the homeomorphic graphs, two different homeomorphic graphs. Already you know what you mean by homeomorphic. You know the elementary subdivision, you know the subdivision, then you know the homeomorphic graph. Homeomorphic from G is nothing but it is a subdivision of G. Okay. So if this is the graph, what we did, same graph we can consider. You may insert vertex of degree 2 between the edges. Or you can say we have deleted this edge, we have introduced a new vertex and we have joined the end vertices of that edge. So like that you can introduce a vertex of degree 2 between the edges. So this is one graph which is homeomorphic with the graph G. This is the other graph, same graph we have considered. The thing is that this edge is deleted. Instead of that, one vertex is added. Okay, then this vertex is joined with the end vertices of that edge which you have deleted. It implies indirectly you are introducing one more vertex between this edge. So therefore, these two graphs are homeomorphic with the given graph G. You can add, here we have added one more vertex between this edge, between this edge, between this edge, like this, even between this edge also. So even you can introduce some vertices between these two edges also. Okay, so that the resulting graph is also homeomorphic with the given graph G. Here the graph is K4. So these are the two homeomorphic graph with K4. You can recall one result by considering this example. If G is a planar graph, then the resulting homomorphic graphs are also planar, isn't it? Definitely you can conclude in that way. Okay, so consider another example. Show that the Peterson graph is non-planar. So Peterson graph, it is a kind of a graph like we have got Kuratowski's graphs. K5 and K33 are considered as Kuratowski's graphs, like that. Peterson graph. So this graph is called Peterson graph. Inside one cycle C5, outside another cycle C5. You know the cycle C5 is isomorphic to itself. Means if this is the cycle C5, if I ask you to draw its complement. So the cycle C5 is self-complementary. If I ask you to draw the self-complementary graph or the complement of C5, you will get this kind of graph. Okay, so outside one C5, inside another C5. But this C5 is like the complement of the C5 type. Then join the vertices on the border. So the resulting graph is called a Peterson graph. Okay, now the question is what you have to do? You have to show the Peterson graph is non-planar. Okay. First of all, to show this as a non-planar graph, what you need to do? See, here one crossing is there. Here also crossing is there. Here also crossing is there. It implies the edges are intersecting. 1, 2, 3, 4. Okay. So try to draw this without the intersection of edges. Okay. So what we will do? We consider another representation of the Peterson graph, which is shown in the figure 6b. Suppose we delete the edges V3, V4. Here V3, V4. You have to delete the edges V3, V4. Okay. Delete the edges V3, V4. Then similarly, you have to delete the edge V7, V10 from the graph of figure 6b. The resulting graph is a subgraph homeomorphic to K33. Hence, the Peterson graph is non-planar. So, if you observe this graph, it is like K33 only. This graph is K33. How many vertices are there? Of course, the K33 contains 6 vertices. But what I am saying, if you draw a K33 type, this is K33 type. Okay. Right. but it is not exactly K33. Some edges are deleted, or you can say we have introduced some vertices between the edges. Okay, so totally the number of vertices are 10 and the number of edges 5 plus 5 10 plus 5 15. So like that you can adjust the edges and you may redraw. You will get a graph which is homeomorphic to K33. Hence the Peterson graph is non-planar. Okay. So in this way you can solve some more examples by referring the exercise or some question papers. Okay. So what we have discussed in this class, we have discussed some problems based on planar graphs. Okay. And of course planar graphs you can say. Preferably homeomorphic to some other graphs. Okay. So with this we conclude today's lecture. Thank you.